students. In this video, we will discuss some applications of greatest integer function. I hope the concept of greatest integer function is clear to all of you. So let us revise for a minute that value of greatest integer function is greater than equal to x and strictly less than x minus 1 for x any number. And the highest power of p that divides n factorial. This exponent is given by summation I from 1 to infinity n upon p power I. So this is the greatest integer here. So let us use this result to find the highest power of 5 dividing 1000 factorial. So we directly use this application here. The highest power of 5 that divide 1000 factorial is given by summation k from 1 to infinity n upon p power k. And as here, how much is n? 1000. And what is p? 5. So putting the values, k from 1 to infinity, 1000 divided by 5 power k. Now as this is infinite sum, but when denominator cross 1000, the value of greatest integer becomes 0. So that means ultimately this is a finite sum. Let us expand this. First is 1000 by 5, 1000 by 5 square, 1000 by 5 cube, and 1000 by 5 power 4, 1000 by 5 power 5, which crosses 1000, and all other terms after this will be 0. And here we can easily divide this. This is 200, and here this is 40 plus 8, and but here we are left with 8 by 5, and the value of this is 0. So very easily, value of greatest integer of 200 is 200, 40, 8, and greatest integer of 8 by 5, this is 1 point something, and the integer towards left is 1. So adding all these values, answer is 249. So 5 power 249 divides 1000 factorial. Next question is, find all n for which n factorial ends with 37 zeros. So we have to find that value of n for which n factorial ends in 37 zeros. So very easily we can get an idea that 10 power 37 will divide n factorial. 10 power 37 will divide n factorial. If 2 power 37 into 5 power 37 divides n factorial. So which may further be written as 2 power 37 divides n factorial and 5 power 37 divides n factorial. But 2 power 38 does not divide n factorial, and also 5 power 38 does not divide n factorial, because otherwise we have 38 zeros. If both of these divides n factorial, then we have 38 zeros. To avoid that condition, we have taken that 38 power will not divide n factorial. But as from the definition, summation k from 1 to infinity n upon 2 power k and summation k from 1 to infinity 5 upon n upon 5 power k, and very easily we can check that number of terms here will be strictly greater than number of terms here. Why? Because here denominator will rise in a higher order. So here we will get more terms in the summation, but here we will get less terms as compared to the left hand side. So this sum will be greater than this. So from here we can focus on only the power of 5, because now this is clear from here that power of 2 is more than power of 5. That means we will only concentrate on the power of 5. So that power which divides n factorial. Let us try to find n. And here we can easily see that GCD of greatest integer of n by 5 should be less than equal to 37. It cannot cross this power. So from here we can find n is equal to 5 into 37, that is 185, which means value of n should be less than equal to 185. So we have to take some value by hit and trial method. Let it be 150. Let it be 150. Let us try to find what power of 5 divides 150 factorial. What value of this divides 150 factorial? That is 150 by 5 plus 150 by 5 square plus 150 by 5 cube. And how much is 5 cube? 125. And after this all terms are 0. Let us find this. This is 30 and 25 divide this, you will get 6 plus 150 by 125, 1 point something, and the answer is 1. See, we get 37. We get 37. Let us find for some other value 155. So how much is the power? 155 by 5, 155 by 5 square and 155 by 5 cube, because hereafter also we get denominator greater than the denominator and all terms will be 0. And after solving this, this is 31, 6 plus 1, that is 38. As you see, when we take 155, we will cross this, but this is not possible because 5 power 38 does not divide n factorial. Okay, let us check for some less value, 149. How much is the power of 5 that divides 149 factorial? 149 by 5, 149 by 5 square, 149 by 5 cube. And very easily we can find these greatest integers. This will be 29 and the value of this is 5 plus 1, that is 35, which is again less than the desired value. So from this we get a range for which n factorial ends in 37 zeros. And what are those values? Greater than 150 and less than 155. So that means n will lie in 150 and 154. So this is the desired value of n for which n factorial ends with 37 zeros. So next numerical, given a positive integer capital N, show that this is equal to 1 and mod of this is less than equal to 1. Let us solve this numerical first. And as from the previous results, we know that for Fn equals d divides n fd. So we have a result that summation small n from 1 to capital N f of n is equal to n from 1 to capital N small of n greatest integer of n by n. So we make use of this result here, taking small fn as mu of n and capital F of n as a function whose value is 1 and 0, 1 for n is equal to 1 and 0 for n strictly greater than 1. Very easily we can verify that, as we know that summation d divides n mu of d is equal to 1 and 0 for n is equal to 1 for n strictly greater than 1. So that means this will justify this, and if this is true we can write this result, and here it is summation n from 1 to capital N, what is small f, mu of n greatest integer of n by small n equals to this n from 1 to capital N f of n. Now let us expand this. This will be f1 plus f2 so on f of n. Now f of capital N. So as from the value of capital Fn is 1 only for n is equal to 1, and for all other values it is 0. So let us put these values 1 plus 0 plus 0 plus so on 0. So answer is 1, which is the desired right hand side, as proved. Now let us prove second part. So we have to prove this. So again we make use of this result here again. Now first of all, as we want to prove from n from 1 to capital N, for small n, for capital N is equal to 1, what is the value of this summation? N from 1 to capital N mu n by n. So putting capital N is equal to 1, you see only one term will be there, mu 1 by 1, and as mu 1 is 1, its value is 1. So result holds for capital N is equal to 1. Now let us prove for n strictly greater than 1. Let us prove for n strictly greater than 1. Mu of n by n. And very easily we can write it as, now because n is positive, we can multiply and divide by n. We can multiply and divide by n. So also, as it is positive, it can be written outside of the mod. And at next step, what we will do, you see, we will add and subtract greatest integer of this, mu n minus its greatest integer. We will add this as well as subtract this, and mod closed. Now very easily we can separate this into two parts, that is 1 by n mod n from 1 to capital N mu n n by small n minus greatest integer plus summation n from 1 to capital N mu n greatest integer of n by this. Now very easily, as you see, this we have already proved in the first part. How much is this? 1. This is 1. So putting its value from here, so we are left with 1 by n mod 1 to capital N mu n n by n minus greatest integer of this, and here we have 1 into 1 by n, that is 1 by n. And at next step, we can easily write the property of mod, that this is less than equal to 1 by n summation of n from 1 to capital N mod of mu n into n by n minus this plus 1 by n. And as we already know when n is equal to 1, you see this will be capital N minus and greatest integer of capital N is n. So this will cancel out for n is equal to 1. So for expanding for n is equal to 1, and we are left with n from 2 to capital N. Mu n by n minus greatest integer of this plus 1 by n. Now, as we know that mod of mu n is less than equal to 1, and also how much is this? So as you see, this is a number minus its integral part. We are left with fractional part, and fractional part is always less than 1. And this term may be written as, further written as 1 by n summation n from 2 to capital N mod of mu n into mod of n by n minus greatest integer of n plus 1 by n. So as we have already seen, this means mod of mu n into n by n minus greatest integer of n by n is less than 1. So converting this into this form, taking the summation n from 2 to in capital N mu n, because this is always positive, strictly greater than 0 and strictly less than 1. So that's why we have written a round bracket here, is less than, and also summation n from 2 to capital N here. And how many ones will be there? 2 to n. That means n minus 1. Now dividing both sides by n. N from 2 to capital N mod of mu n into n by n minus capital N by small n less than, to divide by n, what we are left with, 1 minus 1 by n. So taking this 1 by n to left hand side, 1 by n, n from 2 to n mod of mu n by n minus this plus 1 by n less than 1. So as you see, we will have this term, whole of this term. And what we have proved, this is strictly less than 1 for n strictly greater than 1. And we already proved this is equal to 1 for n is equal to 1. So combining, let this be 1, this be 2. So combining 1 and 2, we can easily write that this is less than equal to 1. So I hope you got the proof. We start from here and solving the inequality, we reached here, and combining these two we have this, because here by 1 we have equal to 1 and by 2 we have strictly less than 1. Next question is, show that the exponent of highest power of p dividing p power k minus 1 factorial is this. Now to prove this result, we need another result, that is exponent of p dividing n factorial is given by n minus ak, ak minus 1 plus so on, a1 plus a0 divided by p minus 1. So we need this result to verify this. So let us start. So first of all, we write the factorization of p power k minus 1, and very easily we can write it as, this is p minus 1 into p power k minus 1 plus p power k minus 2, so on p plus 1. So very easily, if you multiply these two, we will get this. All other terms will cancel out. Now if you expand this product, what it becomes? P minus 1 into p power k minus 1, p minus 1 into p power k minus 2, and when you multiply by p, what we have? P minus 1 into p plus p minus 1. Now using this result, exponent means power of highest, power of p in p power k minus 1 factorial is equal to, so using this, how much is n here? P power k minus 1 minus, so what are these? These are the coefficients. These are the coefficients, as you see here. So what are this? P minus 1 plus p minus 1, so on. How many times? K times. K times. And divide by p minus 1. And very easily, how many times p minus 1 appears? K times. And what is the sum then? K into p minus 1. That is p power k minus 1 minus k into p minus 1 upon p minus 1, which can very easily be written as p power k minus p minus 1 into k. We are putting it in the desired form. So we will get this answer. Now here is an application of this. The highest power of 3 dividing 80 factorial. So let us make use of this result here. So very easily 80 can be written as 3 power 4 minus 1, 81 minus 1. So when you compare with this, so it is p power k minus 1. How much is k here? 4. How much is k here? 4. So putting values here. So the highest power of 3 dividing 80 factorial, p is 3. 3 power 4, 3 minus 1 into 4 minus 1 upon 3 minus 1. So when we simplify, 81 minus 2 into 4, 8 minus 1 by 2. So 80 minus 8, 72 by 2, 36. So which is the desired answer? That 3 power 36 will divide 80 factorial. I hope you got some idea how we can apply various results to solve numericals.